Section 9.1, Trig Identities. We're going to verify trig identities for this section. Remember that an identity is an equation that is true for all values of the variable for which every term of the equation is defined. Now, this next part, you have blanks for each of our identities that we learned in the last section. You should pause the video and take a second to write them down, and then when you unpause it, I'm going to reveal the answers just so that you can check. Now, if you remember the last section, we know the quotient identities, the reciprocal identities, here are the negative angle identities. And then remember that these three identities right here are your Pythagorean identities, and from those we can get these six other identities where sine squared t is equal to 1 minus cosine squared t, cosine squared t is equal to 1 minus sine squared t, and you can do the same for each of the ones below it. So make sure you know all those because that's an important part to be able to verify these trig identities. The next part, identities and proofs. Proving or verifying an equation is not the same as solving an equation. To prove an equation, you have to show it's true for all numbers. The first thing we're going to do is to graphically test to determine whether or not an equation could be a possible identity. So when we're doing this, we look to see if the graphs appear to be the same. And note, this does not prove the equations are identities. To prove an equation is an identity, you must do this algebraically or show algebraically that it is. Now for these examples right here, it says determine if the equation is identity graphically. So we're going to go ahead and for these, because it said graphically, put them into our y equals. Now for this you have to be careful because I can't plug into my graphing calculator sine squared x, it won't let me. So instead of plugging it in like that, we can do parentheses sine x and then the squared on the outside. Those two things for your calculator are going to be equal to the same thing. So in my y equals, I'm going to plug my left side of my equation in y1 and the right side into y2. So 2 and then parentheses sine x close parentheses twice squared minus cosine x. And again, don't forget to close that parenthesis there. And then in y2, I have 2 parentheses cosine x squared plus sine x. And I want to make sure my mode is in radian mode. If it's not, make sure you change it over. And then I'm going to hit zoom 7 because that gives me a nice trig window. So there's my first equation. I guess I should in my y equals also either make it a thicker line by hitting enter, or if you hit enter a couple of times, you'll see this little symbol right here, which will show you where it's tracing over. So now if I hit graph, here's the first equation in y1, and then the next one's going to be the equation in y2. And notice since they're not right on top of each other, I know that it is not an identity, so I can just go ahead and hit the on button to stop it there. So let's go to the second equation example. So for the second example, I have something being divided, so you want to put everything in the numerator in parentheses. So 1 plus sine x, and then plus parenthesis sine x close parentheses twice squared, and then we have to close everything in parentheses again, divided by, and if it helps, put the denominator in parentheses if you want, cosine of x. And then in y2, we have cosine x plus tangent x. And then I'm going to hit on this, make it a circle graph 2 so that I can see if it's the same or not. So here is my second graph. I think I must have missed something. Yeah, I did. So I'm missing, I forgot to change this to a minus on my paper. It's a minus on your paper, so let's go back. So here's my first equation. And notice my little circle thing is tracing over the first one in y1, so y2 is tracing over that. So that means that this is a possible identity, but in order to show that it's an identity, we have to do this algebraically. So this shows that it could be a possible identity. So these are not identities. And this is a possible So remember, in order to tell something is an identity, you have to algebraically do it. The next part that we're going to talk about is proving identities. Usually there's more than one way to prove a trig identity. However, one way is usually more efficient than another. So just because you solve one of these problems one way, it doesn't mean that it's any right or more correct than somebody else who's sitting next to you solving it a different way. So you and your neighbors might have different answers, but they could both be correct. And that's the case with a lot of these. So what I've done is I've come up with a bunch of helpful strategies that you can use. The first one is know the fundamental trig identities and look for ways to apply them. So that's why I keep saying you need to have these memorized, because on your test and quiz, you're not going to have them in front of you. So if you're always using the identities as you're doing your homework, you're not really memorizing them. You're just using them with having them in front of you. So make sure you have them, memorize them, and try not to use them as you do your homework. For number 2, it says express in terms of sine and cosine. A lot of the time students have an easier time when working with sine and cosine. So if you have like tangent or cotangent, it's easier to put it in terms of sine and cosine. Note which functions are in the final expression you want. Sines and cosine pair up well, as do secants and tangents, and cosecants and cotangents. And the reason that is because of these Pythagorean identities that we have up there. That's why they pair up nicely together. The third one says, if you choose to work with one side of the identity, continuously refer back to the other side to see what you are trying to obtain. It is often better to work with the more complicated side first. When the one side contains only one trig function, attempt to rewrite all functions on the other side in terms of that function. Use Pythagorean identities to substitute for expressions equal to 1. Perform algebraic operations such as factoring, simplifying rational expressions, finding the least common denominator and combining fractions, multiplying by the conjugate, combining like terms, multiplying the numerator and denominator by the same expression to attain an equivalent fraction, replacing a binomial with a monomial, and we'll talk about all these different techniques. The main thing is to not just sit there and stare at the problem, just try something, because even paths that lead to dead ends can still give you insights. Now, let's go ahead and practice some of this. Now, again, note, proving identities is not the same as solving equations. Properties that apply to equations such as adding the same value to both sides are not valid when verifying identities, because the beginning statement to be verified may not be true. So the key point when you're solving these is that what you do to one side, you can't do to the other side. You can't move something from one side to the other. So number 1 is just an example of simplifying, and it says write in terms of sine or cosine. So this is what we did in section 6.5. So let's just go ahead. I would pause the video and see if you can simplify this on your own, and then unpause it, and we'll do it together. All right, for this first one, we have cosecant x plus cotangent x times 1 minus cosine x. So we want it in terms of sine and cosine when we're simplifying it, so that's the first thing I'm going to do. I know that the cosecant of x is 1 over the sine of x plus the cotangent, which is going to be your cosine x over sine x, and this is all multiplied by 1 minus cosine x. Now, for this, whenever I'm simplifying it, I want to get all the terms together and combine them. I have two fractions here for the first binomial, so I want to combine them. Because they have the same denominator, I can do that. So I have 1 plus cosine x over sine x times 1 minus cosine x. How do you multiply some fractions? You multiply the numerator times numerator and denominator times denominator. And in this case, I have 1 plus cosine x times 1 minus cosine x in my numerator, and then sine x times 1 in my denominator. So for this, I have 1 plus cosine x becomes 1 minus cosine x plus cosine x minus cosine squared x all over sine x. I just made it a little bit smaller for me. So now I want to combine my like terms. So negative cosine x and cosine x are like terms, and they cancel each other out. So then we have 1 minus cosine squared x over sine x, and then I'm going to think about my identities. Is there any identities that you, when you look at this problem, that you could replace with? So if I go back to my identities and I look at them, well, notice that 1 minus cosine squared t that we have is really right here, the sine squared t, so I can replace that with sine squared t in my equation, which is what I'm going to do. So in my equation, I get sine squared x over sine x, because remember 1 minus cosine squared x is really sine squared x. This allows me to get it into one term, which is what we wanted, and sine squared x over sine x is just equal to sine of x. And then that would be my simplified answer. So again, we got it down to one term and we got it down to sine. The next one is a little bit different. So this one should say verify or prove that 1 plus sine x minus sine squared x over cosine x is equal to cosine x plus tangent x. Now, as I said before, this is not the same as solving equations. So I can't get rid of what's in my denominator here by multiplying both sides by cosine x. That would be a no-no, because what you do to one side, you can't do to the other. You have to keep each side separate. So that's the kind of stuff that I'm talking about when you can't solve like if you're solving an equation. The best thing to do for these problems is to draw a line down your paper so that you know you have to stick to one side. Now, as I said before, there are usually multiple ways to solving these problems. And usually it's not, one way is not more correct than another, it's just one way could be more efficient. Now, it's easier to work with a more complicated side. So if I look at this problem, I would probably think that the left side of my equation is more complicated than the right. So I'm going to start there. If I look at the left side of my equation compared to the right side, well, I notice that I don't have a denominator in the right side. I also notice that I have cosine x and tangent x. Well, remember, tangent x is really sine over cosine, so we're going to kind of use that to help us. Now, for this first one, I would look in my numerator to see, do I see any identities that I can use? Well, I do. I could change that 1 if I wanted to into the Pythagorean identity, which is sine squared x plus cosine squared x, or I have 1 minus sine squared x, which is equal to cosine squared x. That's another thing that I can do, so just try one. I'm going to change the 1 minus sine squared x, and then we have plus sine x. I'm going to change that into cosine. So 1 minus sine squared x, we're going to replace with a Pythagorean identity with cosine squared x. That's where that comes from. And this would be plus the sine x over cosine x. And then I notice I have two terms on this side, so I'm going to separate these two by separating the first one into cosine squared x over cosine x, and then plus sine x over cosine x. And notice when I did that, well, cosine squared x over cosine x just becomes cosine of x, because it simplifies. So we have cosine x plus, and sine over cosine is tangent x. And notice that this side now equals that side, so we are done. Now, let's say that I didn't want to do the left side first. Let's say instead I decided to do the right side. So this would be another different way that you could have done the problem. So let's say I started with the right side and I want to get this into the left side of my equation. Well, I would notice that my terms are combined, so then I would probably want to combine my cosine and tangent. So the first thing I would do is write it in terms of sine and cosine. So this is the cosine of x plus sine x over cosine x, and then I would say, well, how would I combine those? In order to combine those, I need a common denominator. So what's common between cosine x and 1? I would have to multiply this by cosine x over cosine x. And this does not change my equation by doing that, because cosine x over cosine x is like multiplying your equation by 1, so it doesn't change it. Now when I do that, I get the cosine squared x over cosine x plus sine x over cosine x. And then I can combine my numerator over my common denominator, which is cosine x. So cosine squared x plus sine x over my common denominator, cosine x. And then I would go back to the other side of my equation and notice that there is no cosine squared x in my numerator, but I remember the Pythagorean identity, sine squared x plus cosine squared x equals 1. So that means I can replace cosine squared x with 1 minus sine squared x, because I know the identity. So that's the next step I'm going to do. So cosine squared x is 1 minus sine squared x, I just replaced it, plus sine x over cosine x. Now I have the same thing in my numerator and denominator as on the other side of my equation, but it's not in the same order, so I just need to rewrite it. So 1 plus sine x minus sine squared x over cosine x. Now this side checks out with this side over here. So I did the left side of my equation one more way, which is right down here. Now instead, remember I said I could replace the 1 with sine squared x plus cosine squared x. I did that, and then I cross out sine squared x and sine squared x because those were like terms and they cancel each other out. And I got cosine squared x plus sine x over cosine x, and then I separated it because it was separated on the right side of my equation, and notice that that is another way of that I could have solved the problem. So as I said before, that one way isn't better than another, it's just that usually one way is more efficient, and in this case all three ways would have really gotten you to the same place at the same time. And remember, you only work with one side, and you really need to keep each step written out because that's why we're doing these. We're trying to verify, so somebody needs to be able to follow each step. That's why you notice I keep it in a nice straight line going down so that I can follow each step that I'm using. So this right here was just another way to solve the problem. So I'm going to group that together and just move that over here. I'll make it a little smaller. And I'm going to move that over here. So that was another way. Whoops. Okay, now let's do number 3. Number 3 says we want to prove sine x over 1 plus cosine x equals 1 minus cosine x over sine x. Now for this, both sides look equally complicated, so it doesn't really matter which side you want to pick. I'm going to go ahead and pick to work with the left side. On the left side, I'm going to draw my line going down first, and then I have the sine x over 1 plus cosine x. I don't have any reciprocal identities, and I don't have any tangents or cotangents to change into sine or cosine. So if I look at the right side of my equation, I notice that the numerator is 1 minus cosine x, whereas the denominator here is 1 plus cosine x. So what I can do is use some algebra, and I can multiply by, and if you look at these, this right here are conjugates, because remember conjugates, you change sign at second term. So 1 minus cosine x over 1 minus cosine x, I'm allowed to multiply that by the conjugate here because it's like multiplying by 1, and it's not going to change my equation when I multiply by 1. So then I want to distribute in my numerator. So this would become sine x minus cosine x over, and then I'm going to FOIL my denominator. So 1, and then I have minus cosine x plus cosine x minus cosine squared x. Notice I write every step out when I do this. Negative cosine x plus cosine x ends up canceling out, and I'm left with, in my numerator, sine x minus cosine x, which I really didn't have to write it like that. I probably should have kept it without distributing because this is how it is in my numerator, so I'm going to go back to how it was. So I have sine x times 1 minus cosine x all over 1 minus cosine squared x. And then if I keep on going, I have in my denominator here sine, and notice that 1 minus cosine squared x, if you remember from your Pythagorean identities, is really sine squared x. So I have sine x times 1 minus cosine x all over sine squared x, and sine x over sine squared x is really the same thing as doing sine x over sine squared x times 1 minus cosine x. That's what we're doing. You don't really need to write that part out if you don't want to. So that just simplifies into one of your signs cancel out. So this sign cancels out with one of these signs, and you're left with 1 minus cosine x. I should really write this underneath. So 1 minus cosine x over sine x, and now you'll notice that this side now equals this side, so we are done. So another way that I could have done this problem is instead of doing the left side of my equation, if I would have done the right side, I would have multiplied by 1 plus cosine x over 1 plus cosine x. You're allowed to do the conjugate of the numerator. If I do that, then for this problem in my numerator, I get 1 plus cosine x minus cosine squared x all over sine x times 1 plus cosine x, and again I didn't multiply that through because it's 1 plus cosine x in my denominator on the other side. And then when I do this, these two terms cancel out because they're like, and plus and minus 1. So then we get 1 minus cosine squared x over sine x times 1 plus cosine x. I need to cancel out that sine x, and I notice my numerator needs to be sine x, so 1 minus cosine squared x, remember the Pythagorean identity, that's really sine squared x over sine x times 1 plus cosine x, and then one of these sines cancel out to leave you with sine x over 1 plus cosine x. So that's what I was saying before, that, sometimes it's not easy to see which side to do, but both sides end up resulting in the same thing depending on which side you pick. Now, let's go ahead and do one more for further notes. It says prove cosecant x minus cotangent x equals sine x and then over 1 plus cosine x. For this problem here, it doesn't really matter which side you want to use. Let's go ahead and do the left side of my equation. If I do the left side of my equation, I notice that this side is all in terms of sine and cosine. Because that side is all in terms of sine and cosine, it probably would be helpful to take the left side and put it in terms of sine and cosine. So cosecant is 1 over the sine of x minus the cosine of x over the sine of x, because that is the cotangent quotient identity. And then because they have the same denominator, I can rewrite that as 1 minus cosine x over sine x. And then, oh wait, look at the problem that we just did. Isn't this the same problem where we had this was equal to this side over here? So then I would do everything that I just did in my last problem. So the next step that I would do here is I would multiply this by 1 plus cosine x over 1 plus cosine x, and then I would get 1 minus cosine squared x in my numerator over sine x times 1 plus cosine x, and then I know by my Pythagorean identity that 1 minus cosine squared x is really equal to the sine squared of x, so then that would help me see that I can write sine squared x over sine x times 1 plus cosine x, and then one of your sines cancel out to leave you with sine x over 1 plus cosine x. So that's one way that we could solve the problem. And again, there are other ways as well. Now, what we're going to do in class is we'll do number 5 and this should say number 6 right here, not 5. But what I suggest you do before class, see if you can do these on your own, because the best way to do these problems is to practice it. And like I said before, sometimes one way might lead you to a dead end, but at least it's doing something, and usually dead ends will help you figure out how to solve the problem by going back and looking at it and say, okay, this didn't help me, but maybe instead of doing this identity, if I substitute it with something else, that will help me out. So see if you can do these, and then we'll go over them in class.